Okay, so we had some material from last time that was left over. I'm going to finish that. That's on monitors. Then we'll switch to other synchronization problems for today. So just to recap first, we talked about semaphores and monitors last time. I talked about what is a semaphore. It's essentially a special integer that's used for synchronization, whose value can only be changed through atomic operations called wait and signal. Wait decrements the value of a semaphore atomically, signal increments the value of the semaphore. We saw that semaphores could be used as a lock. Okay, that's also referred to as a binary semaphore. You can generalize it to do more than what a lock would do by initializing it to n, and it would then protect n resources of the same type. Okay. And then the last but not least, we saw a third use of semaphores, okay, in addition to being used as a lock and to protect n values, which is to specify scheduling constraints. Okay, I showed examples by which you can use semaphores to control the order in which code can execute. Okay, if you want certain code in a thread to execute before certain other threads, and you do not want to depend on the CPU scheduler, which you shouldn't, okay, you will actually have to use semaphores to express those scheduling constraints. And we saw how to do that for producers and consumers. Okay. Then I introduced this notion of a monitor. Okay, and I said monitors are higher level constructs, okay, that allow us to achieve similar goals. Okay, monitor is essentially a class that is protected by an internal lock. Any method of this class, when it executes, is guaranteed that the thread that executes it holds a lock. So you are preventing, actively blocking all other threads from executing methods of this class. Okay, so we'll continue that discussion. I did show you in some sample code for a Q class. Okay, I talked also about Mesa and Hoare monitors, and I said most of the time your Mesa monitors. Hoare monitor explicitly allows you to do a signal and transfer the lock to a thread. Okay, in the Mesa monitor, you just wake up a thread, but you don't explicitly transfer the control immediately. You wait for it to be transferred when the CPU scheduler schedules the thread for execution. Okay. Now what we'll do is we'll continue that discussion and see how do you do monitors in other languages. Okay. Java, things have been made easy for you. You just take in a word, keyword synchronized in front of a method, and your class has suddenly become a monitor. You're not doing anything. You're just telling the JVM saying create this class as a monitor, declare internal locks. Whenever any thread calls a method, make sure there is a lock that you have acquired before the method executes. Okay, so all of the hard work is done underneath for you. Okay, you're not so lucky if you're writing code in other languages like C or C++. There is no synchronized keyword. Okay, you have to actually implement locks explicitly and try to grab them before doing them. Okay. So here is how you would acquire. You see the same code for a queue, but now written in C++. It's a class where you have the same add and remove method. Add adds an item to the queue, remove removes the item. You actually now explicitly declare a lock, okay, because there is no inbuilt support for monitors in C++. And then you're okay. So what you now have to do is wherever you use the word synchronized in Java, those methods you will actually put a lock acquire and lock return, lock release at the beginning and the end. Okay. This is what the JVM would have done internally for you. Okay. In C++, you explicitly write code to do lock acquire and lock release. Okay. So you'll see that Q add has acquire and release, okay, at the beginning and the end, and remove also has an acquire and release. Okay. So now you have to write a little more code. Condition variables are still supported. Okay, as part of the threading library. So you do the same thing. Okay? You put an item on the queue and you signal if there is a consumer waiting and is sleeping for the queue to become non-empty, you signal. Okay? In the remove, you say while the queue is empty, you will wait on the condition variable. Okay? You will go to sleep atomically, release the lock. Okay? So you release the lock, go to sleep, and then you remove the item from the queue once that condition has actually become true. Okay, so this is how you would actually implement the same class in C++. Okay, where you have to write a little more code because you don't have built-in support for monitors. Any questions on this? Yes, question.
How are these monitors locked? Just locks.
Okay, wouldn't these be just locks? They are indeed locks, but you are using condition variables. Monitors are intimately tied to condition variables. condition variable is a construct where you can go to sleep and release the lock atomically, right? So that part is still supported, but mutual exclusion is not automatically supported. You have to decide what part of the code. In Java, the entire method is always protected by lock. In C++, you don't have to do that. I just showed you a straightforward translation where you do protect the entire method, but you don't have to. You could protect some smaller part of the code and some other part may run concurrently. So you have a little more flexibility. In Java, it's all or nothing. You either protect the whole method using synchronized, or you don't put synchronized and the method has no protection using the lock. Here you can decide where you put the acquire and release. By default, if you put them at the beginning and the end, that's same as what you do in Java. Okay, so this is the same implementation using bounded buffer. Okay, producers and consumers, they have a shared buffer of size n. Okay, so now you have to have two scheduling constraints. If you remember, if you have bounded buffer, you have producer and your consumer. There are two scheduling constraints. Okay, what are they? Anyone remember? Yes.
Consumer cannot consume while the queue is empty.
Okay, first thing is you cannot consume something until a producer has produced something. Okay, yes, sir. Okay, so producer cannot produce anything if the queue is full. Very straightforward thing. The queue is empty, there's nothing for the consumer to do. The queue is full, the producer shouldn't do anything because you cannot actually stick that into the queue. Okay, so we'll use two condition variables to specify these scheduling constraints. Remember when we did semaphores, we did a lot of complicated things using semaphore. Here life is very simple. Okay? You will essentially have two checks. Okay? If the queue is full, okay, count as the number of items in the queue and you can have up to n items. If the queue is full, go to sleep. Condition variable says just put this to sleep and something else will wake it up. Okay? And the consumer is going to do exactly the other one. If the queue is empty, okay, there's another different condition variable, also go to sleep and release the lock. Okay? So all of that complicated things you saw with semaphores becomes very simple. The scheduling constraints are very straightforward to express. Right? You just basically check for the condition, okay, and then you go to sleep if the condition is not true. Okay? Now I will mention that this is Hoare-style, which is why this is an if. If this was real Java code, you would make this a while. Okay? We talked about that last time. So you will say while the condition is true, go to sleep. Okay? And the rest is the same. So all you have to do is make sure now you go beyond this, you are guaranteed that you don't have a full queue. So you are just going to produce a data item, stick it in there, and then you try to wake up any consumer that may be sleeping. Because if the queue was empty, there may be a consumer sleeping. So you always do a signal on the other condition variable. So here this consumer is sleeping. The producer will wake it up after it produces a data item, and here the consumer will wake up a producer that is sleeping. Okay? So you basically do a signal in the other code, and you're done at this point. Okay? So now we just basically use the same logic as we had in semaphores, much more simplified. The scheduling constraints are simply expressed by a while or an if statement. If it's a regular monitor, you just say while you want to check for that scheduling constraint, and if the constraint is not true, you just go to sleep using the condition. And after the condition becomes untrue, somebody else wakes you up using a signal. If you're sleeping here, the producer wakes you up saying, I produced a data item. A fairly straightforward implementation. This is again C++, which is why you have this lock, acquire, lock, release. In Java, you wouldn't have these two lines of code. You would just write synchronized here, and these things would be done automatically for you. But the rest of the code you still have to write. Okay? Any questions on this? Okay, so last point of discussion before we move on to sort of more synchronization problems is just to understand the difference between a semaphore and a condition variable. Okay, as you have realized probably, a condition variable has a wait and signal, and so does a semaphore. A semaphore also has a wait and signal. So you could ask internally, are they the same things? Why we just call them two different things? Okay? In other words, if I had a semaphore, would I just write a condition variable wait as a semaphore wait and a condition variable signal? Can I implement that in a semaphore signal? Are they the same thing, or is there a fundamental difference between the condition variable and a semaphore? They seem to have the same methods called wait and signal. They sort of seem to do the same thing. Wait causes blocking, signal causes somebody else to wake up. Okay? So you have to ask the question, why is this the case? Is this intentional? Are they the same thing? If not, what's the difference? Or if they're the same thing, why are they even called two different things? Why did we not just call it a semaphore always? Okay, so that's what we want to discuss. But so I should have pointed to that code. So is that the right thing? Is this condition variable simply a semaphore and just calling a wait on an internal semaphore, right? So let's ask the question. So first of all, I'm going to write some stuff on the board here. So this is a condition variable CD. This is a semaphore. Yes. These are the methods supported by condition variable. This is what. So now let's ask some questions about whether they are similar or different. So first of all, if somebody has any thoughts about this, let's see what, if any of those might be. So do you think they are doing the same thing? This way to put you to sleep, signal, wake you up. Conceptual. Okay, so let's ask the following question. What does semaphore wait on a semaphore do? Okay, we studied that last time. What does a wait do? Yeah. Okay, it decrements the value and then also does a check after that. That's what okay. So wait decrements the value of the semaphore. Semaphore is an integer. And if the value goes negative, you block. Okay. What does condition variable wait do? Yeah. It releases the lock and goes to sleep. That's what we said it does. It atomically puts the thread to sleep. Okay. Here you decrement, so this is the way we defined it. You decrement the value of the semaphore. If the value is negative, you put the thread to sleep. Here, you put the thread to sleep and release a lock. Okay. So do you see any difference between the two? Or are they both doing the same thing in terms of putting threads to sleep? Yes.
You need to switch.
Would you need to switch the order? So let's come to the order in just a moment. I'm just saying we put up two definitions of wait, right? One for a semaphore and one for a condition variable. I'm simply asking, do you actually see a difference or do you think they do the same thing? Because we just defined it. So I'm re-asking the question I just asked. And do you see any difference between the two or would you hypothesize that they are exactly the same? Anybody have any guesses on this? Yes.
I think condition variable communicating each other without meaning.
Okay. So you are talking about how they implement it, they communicate with each other without a medium. Okay, that's fine. Any other thoughts? Okay, so I will write some code now. This is going back to the order and we'll see what happens and then maybe we can come back and ask whether they're the same or not. Okay? So let us basically assume that there is a piece of code that is going to say and then later on you do this. And here okay, so let's say what's going to happen here. When you execute the signal, what's going to happen? Sorry, what did you say?
You'll increment the count.
Okay, so condition variable, we never said anything about a count. That's for that. Okay, so what you said is true. Here, when you do signal, you'll increment the count. Okay? When you do wait, it will decrement the count. That's what condition variable and signal do. Okay? So but I didn't specify the initialization here. Always you should ask, what does it initialize to? So we'll say, let's say semaphore is initialized to 1. Here you go, you increment it. Here you go back and decrement it. Okay, so this will not cause it to block. Okay, because the value is not negative, so you just continue. Okay. What happens here? Okay, signal basically says if there is a thread blocked, wake it up. Let's assume there are no threads blocked, so it's just going to simply look for any blocking thread. There are none, so it's just not going to do anything. And then when you do wait, what happens?
Release the lock and block.
Okay, wait always blocks. You just said you release the lock and you block. So here, okay, yes.
But when condition variable.signal is called, isn't the semaphore.signal method called in incrementing the count of the semaphore?
Okay, so now we are asking a question, when you do a signal, isn't it calling the underlying semaphore? See, we never defined how some condition variables are implemented. We just said what condition variable, we just defined it in the abstract way, which says whenever you call wait, you release the lock and you block. Whenever you call signal, if there is a blocking thread, wake it up. Otherwise, do nothing. That's what we said. Okay, we didn't say there was an integer. Here, we explicitly defined an integer. When we said you increment, you decrement, and so on. Here, we didn't say that.
I'm sorry, I was going off that, which isn't.
No, this is
quite-
just code to ask you whether this is the way you would do it.
Sorry.
This is a wrong code. It's
Okay.
not the way you would do it. This was just a way to explain to you what the definition tells us should happen. Okay? So what they should tell you is the following. Semaphore has a state associated with it. That's the value of the integer. It is keeping track of who has done signal, who has done wait. Okay, so when you do signal, you increment it. So it's tracking that somebody did a signal and incremented. And when you do wait, you decrement it. Okay? Here, there is no such state. Okay? So signal just looks at, is there a thread waiting now? If so, wake it up. Otherwise, do nothing. Okay? The fact that afterwards, if somebody does a wait and there was a previous signal is not actually being recorded anywhere. Okay? So in fact, this code should tell you that condition variables and semaphores are not the same, because if you actually write condition variable signal followed by a wait in a piece of code, and you write signal followed by this one, in this case, you will always block here. It doesn't matter whether this signal exists or not. Okay, because this by definition is going to cause you to block. Here, whether you block or not depends on the signal and the initialization. Okay, is that clear? What I said, yes.
So if you had the semaphore initialized to 0, then will both work the same?
Yes, so if, in fact, it will work if you do the opposite. Right? So here you will block, this is assuming if you do the signal in a different thread, you will unblock this thread. Okay? Here you wait, okay, let's say you had a 0. Okay? Here you will again block. And then this will unblock it. Okay? So if you have the wait coming before the signal, they do behave the same way. Okay? If you have the signal coming before the wait, they don't behave the same way. Okay? Because in semaphore, the signal is actually going to increment the value of the integer. So a later thread will actually see that incremented value and act accordingly. In the case of a condition variable, if the signal, there is nothing to unblock, the signal is lost, it's ignored. Okay? A later wait is not going to say you did a signal, so I am going to not wait. Because wait by definition always says you sleep. Doesn't matter who did a signal before. You sleep until the next signal. Okay, is that clear? That there is actually a difference between the two. Although they seem to have the same wait and signal methods, they are not the same. The condition variable wait, you always block. It doesn't matter. In a semaphore wait, whether you block or not depends on the value of the semaphore. Okay, that's how we defined it. You decrement if the value is negative, only then you block. Right? That means sometimes weight will not cause you to block, and sometimes it will cause you to block by definition, depending on the value. The value is non-negative, you will not, weight won't block. Okay? In a condition variable weight, you always block and release the lock. Right? It doesn't matter, there's no such value you are tracking. Okay, so you have to keep this in mind that semaphores and condition variables, although they are the same method, they are not exactly the same. Okay? Is that a good enough convincing argument? So in some sense, this code is actually wrong. Okay? This is not the way you would actually implement condition variables using a semaphore. Okay? You have to do something more complicated, which is, so I already said all of this. This is the way, if you can implement condition variables using semaphores, but you are not going to do this. Okay, that is the wrong way to do it. You won't say condition variable weight as a semaphore weight because they are actually different things that define differently. You have to track what's going on. I won't go into the code here. Okay, there's actually 2 pages of code. Okay, so here is how you would implement condition variable weight. You will track how many threads are waiting, and you will suspend the thread if you always have to block in the condition variable. So you always suspend the signal. You will actually check if somebody is waiting, then you unblock it. Otherwise, you're just going to ignore the signal. Okay, so that's basically what the implementation says. I will not go into too much details here because the concept I already mentioned. The only thing you really have to remember is in condition variable weight is always going to sleep. It's not conditioned on anything. There's no value that you are tracking. Semaphore weight, you will block depending on the value of the semaphore or not. If value goes negative, you block, otherwise you don't block. So there are chances that you call a wait and you'll just come out of the wait and start executing immediately. Okay, so this is what you should remember. Okay, so I'm going to stop and take a break here. We are going to go into some more intricate synchronization problems, but we finished the last lecture, so I will start today's lecture with a story. Okay, it's an apt story. As you will see, a story is about an archer who's getting trained in a forest. Okay, it actually comes from an Indian epic, which I won't bore you with. I'll just recite the parable. Okay, so the story is there is some students learning archery, okay, in a forest, and then the first student goes and he has to hit an arrow into a bullseye, and then the teacher asks him, okay, what do you see in front of you? So this guy says, oh, I can see the target, I can see a tree behind the target, I can see the sky, and I can see lots of other things around. So the teacher tells him, okay, go back to the end of the line and think about what you just said. Okay? Next guy comes along and says, what do you see? He says, I see the tree, I see the target, and I see the sky behind it. And he's made to go back to the end of the line as well. Okay? Third student comes along and says, what do you see? He says, I see the bullseye, and I see the center of the bullseye. The teacher says, what else do you see? He says, I see nothing. Okay? Do you not see the tree? Do you not see the sky? He says, no. Right? And the teacher says, okay, now you can shoot, and he shoots, and it goes and hits the bullseye. Okay? So that's the parable. Now you can say, what does this mean? So the story, basically, the parable, the moral is that if you focus, you will hit your target. Okay, if you are going to sort of see 20 things when you're trying to do one, you will never be able to focus and do the right thing. Okay, so the short moral is we stay focused. Okay, and the reason I'm saying this now is you have an exam next week. Okay, so if you start seeing the tree and the sky, you will not hit the exam. So you need to stay focused. Okay. All right. So now we will switch to so that was it for the exam. Okay, lecture 8. We just finished lecture 8. So 1 through 8. Okay, this is going to be on test 2. So you still have to listen. Okay, so what we are going to do now is learn about some other synchronization problem. Okay, we talked about constructs. We did locks, did monitors, we did semaphores. Okay? In doing so, we also encountered the producer-consumer problem. Okay? Producer-consumer is instantiation of a general problem where threads have a shared data structure. Okay? And producers produce, consumers consume. We'll look at 2 additional synchronization problems that also occur frequently. One is called the reader-writer problem, which I'm going to start talking about now. And then dining philosopher's problem is the other one. Okay, so these are three problems that we will sort of encounter as part of our discussion on synchronization. Producer consumer we already did. Okay. Reader writer and dining philosopher we are going to try to cover today. Okay. So reader writer problem is as follows. Okay, so we'll assume that there is a shared data structure. It could be a variable, it could be an array. It doesn't matter what the shared object is. And there are some threads that are trying to read or write to this data structure. Okay? Because it's a shared object, you should immediately say that this data structure should always be protected by a lock. Before you access this object, let's just say it's an array, so I'll just make it more explicit. Before you access this array, you should grab a lock. Once you're done accessing this array, you should release the lock. That is how we have talked about synchronization thus far. Okay? But now we'll try to see, and at the same time, we want to maximize concurrency. You should always realize that whenever you have locks or semaphores or monitors, you are decreasing concurrency in order to achieve some correctness goals. Lock explicitly blocks other threads. So the threads are not concurrent, because concurrency, when you have shared objects, is actually harmful. So if you didn't have locks, all the threads would merely run and you would get maximum concurrency, no blocking whatsoever. But whenever you are accessing shared object or your critical section, you don't want that to happen. The bad things will happen, so you prevent concurrency. Okay? So locks, when you access a shared array, is going to do exactly that. It's going to block other threads. So we are going to ask the question, can we somehow increase the level of concurrency even though you want to access this shared array? Okay? And to understand how to do that, we will say there are two kinds of threads. Okay? We will call them reader threads and writer threads. Okay? Reader threads always read the value of the array, but not modify it. Okay? And writer threads write to the value of the array, meaning they actually modify the value of the array. Okay? And we say if threads were partitioned into these two categories, okay, do you actually have a better way to protect this data structure and still ensure correctness? Okay? Because the lock by definition will not distinguish between a reader and a writer. It will say, if regardless of whether you want to read from the array or write to the array, you will block everyone else while that read or write is happening. You'll always say lock acquire, you'll do either read or write, and then you do a lock release. Okay, so everybody is blocked, meaning whether you are a reader or a writer. Okay. But if you are going to have readers and writers, we can relax that assumption, okay, of having strict synchronization. And what we will say is the following. Okay. Having concurrent reads or parallel reads is okay. We can allow multiple readers to actually read the object because they are not modifying it. It's okay to read. Okay. But if some thread is trying to modify it, is write to it, then you should let that thread alone, one and only one thread, modify that, and everyone else needs to be blocked at that point because you are making modification. Okay? Is that clear what I just said? So you can allow multiple readers, but when you're writing, better let only one writer go, because if someone is reading while you're modifying, you may actually have bad things happen. You may read incorrect data or some such thing. Yes. Okay. So our correctness criteria when you have strict readers and strict writers is let multiple readers go. When multiple readers are reading, no writers can proceed, but you can let as many readers as you want. Okay? When any writer writes, no one else is allowed. No reader or writer is allowed. Okay? So the correctness criteria is guarantee mutual exclusion for writers. Okay? Writer only one at a time. No reader, no other writers allowed. Okay? But when you do reads, allow multiple readers to execute at once. Okay? So because that will increase concurrency. Okay? Because reading is not a harmful operation in terms of synchronization. It's just reading, not modifying. Okay? So you will basically get the same value. Okay? And we still want a critical section. The question is, how do you generalize our notion of a lock to ensure this correctness criteria? Okay, that's what we'll study next. This is referred to as a reader-writer problem. Okay, so let me first pause and ask whether the problem is clear before we jump into the solution. Okay, we are trying to generalize the locks to maximize concurrency. Yes, question.
Are readers allowed to read while a writer is writing? Or is it...
Readers will not be allowed to read if a writer is writing. If a writer is writing, no one is allowed. Okay? So if there are some readers reading, a writer has to wait until they're finished. It will be the only one doing the writing. No readers allowed. And also no writer. Of course, it goes without saying that other writers are not allowed either. Okay? And likewise, any number of readers can read, but while there are reads happening, writers will obviously not be allowed. Yes, question.
Is there a way to check if a lock's acquired without acquiring itself?
Is there a way to check if a lock is acquired? There are ways to check. Okay, so we will look at how to solve this problem, okay, using either semaphores or monitors. Okay, so we'll start with the semaphore version. Yes.
So, if there's like multiple readers reading simultaneously and someone wants to write, do they have to wait for all the readers to finish, or can they kind of say, you have to wait till I'm done writing?
So if there are multiple readers reading and a writer comes along, okay, by definition of our correctness criteria, the writer has to wait until all the readers are finished and then ensure that there's nothing else happening, and it grabs the lock and it starts writing, and it prevents all the other readers and writers.
So, like, when the writer queues up, does that mean no more readers can start reading? Or can they,
Question
does
is,
the writer just sit there and wait
right.
for
So if
more come?
So that's a very interesting question. The question is, let's say there are readers, okay, they are reading. Writer comes along. Writer is blocked, yeah, because he's waiting for the readers to finish. What happens if another reader comes along? Right? So fairness says that that reader has to also wait. Okay? But we see solutions where that is not necessarily the case. You say the writer is blocked, but if the read is happening, let the reader go through, let it do what it wants. And that may not be fair, but that still satisfies the correctness criteria. We didn't say anything about fairness in the correctness criteria. Okay? The correctness criteria said do this and only this. What you said is not specified here, so you have the option. So you can do it or not do it. If you want to be fair, you do it. But an unfair one will still meet this, unfair solution will still meet this criteria. In fact, we'll see solutions that are actually not fair. We'll try to make them a little more. Okay? So all good points. So now let's look at the solution. Okay, so this is the reader-writer solution to the reader-writer problems. Initially, the number of readers is 0, and number of writers you don't need to try, it's only 1. So you have two semaphores, a mutex semaphore that's just acting as a lock, and a write semaphore that's going to control who gets to either read or write. Okay, you initialize both of them to 1. So both semaphores initialize to 1, and here is the write class, and this is the read class. The write class is very simple. Okay, you just do a wait on the write semaphore, okay, which is basically acting as a global lock, essentially. Okay, and so if you're the first writer, nobody else has come along, you go in. Anyone else is going to block immediately. Any other writer will automatically block, because when you do a wait, value is already gone from 0 to 1. Any further writers will only make it negative, so they will just block them. So that automatically guarantees there's only one writer going to go in. Okay. So the code for writers is no different from just using a lock to protect the writes. Okay. So essentially that's what's happening. Code for readers is more complicated, okay, because you want multiple readers. You simply put a lock, it will only ensure one reader goes in. The concurrency is all gone. Okay, so that's not a correct solution. So this is what you do. Okay. You first get a mutex lock. Okay, that's you just do a wait. You increment the number of readers. You are going to track how many readers are actually active in the system. You had 0. This is the first one that has come along. Incremented, it becomes 1. You say, am I the first reader in the system? Okay, if number of readers equal to 1, I am the first reader. Okay. Now it is my duty to prevent any writer from starting up, because I am reading. Other readers can come along. Once reads start, writers are blocked by definition. Okay. So if I am the first reader, I essentially do a write.wait and block writers. Okay. So now the value of the write semaphore was initially 1. Okay. That's what we initialized it to here. Okay. So the first reader is going to come in and decrement it to 0. So now once the reader is in, if a writer comes along and starts decrementing, it will go negative. So all writers are also blocked. Okay. So if I'm the first reader, I block the writers. Okay. And I release this lock, I perform a read. Okay, the read itself is not protected by a lock, as you will see. Okay, in the case, write is protected by a lock. So read, as you can have as many readers as you want. So after the first reader, other readers will come along. They'll simply increment the number of readers. They're not the first readers, and they don't need to do this. They will not. They'll just increment and go and start doing reads. So all the reads will happen in parallel. Yes, question.
If
Yes.
How does the first writer realize it's gonna
Right. So
just to
the first, so what will happen is once you will look through the code. So once you finish the read, you are going to start decrementing the number of readers. Okay? So you keep decrementing. And if I'm the last reader to leave, so just as if I was the first reader to leave startup, I block the writer. If I'm the last reader to leave, I'm going to unblock the first writer by incrementing the semaphore. Okay? So now the first writer that has come in is blocked. It will get to go in. Okay? And you said 2 more came in, so there are 3 of them. So each of them will now, once you finish, you do a signal. So the next one will go in. Because the signal says, is there other writer blocked on that semaphore? That you said there were 3. So each writer is going to unblock the next one. They'll do the read and unblock the next one and so on.
So it only checks the counter when it calls wait. Not so when it calls signal. When something calls signal, it automatically wakes it up across the town. So they don't
That's a semaphore.signal. So signal, we said, always increments the value of the variable. If it's less than or equal to 0, it also says that someone is blocked to unblock them. Right? So that was the definition. Okay, so it should be clear what's happening. The readers, basically you just increment a counter to track how many readers you have. The first reader always has to block all the writers. So when the reads happening, no writers allowed. Okay? And then you do the reads in concurrently. There's no lock protecting this read, so you just go and start reading. And then as each reader leaves, you are going to start decrementing the counter. And if you are the last reader, if the counter has gone to 0, you have to unblock the writers. Because your first reader blocked them, the last one leaving says, now you go ahead, you unblock the writers. And then if writers have come in while the reads were happening, they would have all blocked on that wait semaphore. Each one will be let in and you will perform the write, and then as each writer exits, it will unblock the next one by doing a signal. Okay? So each writer will go one at a time. The readers are going in parallel. Clear? Okay. So that's the logic. There's one small detail which is, why do you need this mutex lock here for this part of the code and this part of the code? The read itself doesn't need a lock. We said reading is parallel, doesn't need a lock at all. So there's no lock protecting the read. But this part of the code where you're checking if you're the first, last reader, etc., and this one requires a lock. So you're protecting it by a mutex lock or a mutex semaphore or binary semaphore here and here. Why is it necessary? Do we need it? Yes.
It's so that the writer doesn't acquire the lock while the reader is
The writer doesn't acquire a lock while the reader is reading. That is true, but that is done here. That is where you block the writers. That's done by this write semaphore. I was simply asking, why do you need the mutex? The write semaphore you clearly need because you are the writers blocking and unblocking. I was asking, why do you need a second one called mutex? Okay, because you don't need it for the reading itself.
If there was no mutex, then during that piece of code, if there was a context switch, it could screw up the value of readers.
Okay.
Two readers go at the same time, you can mess it up, and then you discount it the rest of the time.
Okay, so the point both of you are making is the right one. The count of readers, the integer variable, is a shared variable. Multiple readers are going and mucking with it, they're incrementing and decrementing. Any shared variable, always protect with the lock. Okay? We are not protecting the read itself, but the counter that tracks how many readers are in the system is a shared variable. So if you increment and decrement it, that is, you are accessing it. So you need to protect it by a lock. So this lock is simply protecting the incrementing of the counter and checking if the counter is 1, etc. Okay, so that's a shared variable, and that's what you're protecting. So that's why you need that mutex. Okay. So the mutex here is not protecting the read itself. It's simply protecting this changing of the counter values, okay, incrementing and decrementing of it. Okay, so I won't go into all the detail. There are some scenarios of who blocks and who unblocks. Hopefully it should be clear that the first writer will block everyone, whether it's a reader or writer. Okay, let me ask that. Okay, so let's assume that I said that first reader goes and blocks the writer. Okay, let's ask the question, how does the writer block readers? So let's say you're the first writer. Okay, I didn't do that. Okay, so first writer goes in. Okay, you do decrement write, it goes to 0. Okay, and you're now merrily writing. First reader comes along. Okay, how is the reader blocked by the writer in this code? Yes.
The first person comes in and increments the count, and then when it goes to get the lock, it waits for the writer to be done. And then, assuming it's the first reader, and then every other reader doesn't wait for the lock. It just that.
So the reverse is clear. Readers are explicitly blocking writers, okay, and unblocking writers. But we didn't actually try to ask the question, how is the writer blocking the reader? The writer is blocking other writers because all writers do wait. So first, when the first one goes in, the others block. So how is the writer blocking the reader? Yes.
So the first one, first reader comes in as a writer's writing, gets the mutex, and then increments the count to 1, because the first one's waiting for the writer. And then if more readers come in, it's waiting for the initial reader to wait for the writer to pass the Semaphore for the mutex, and then they can.
Okay, so sort of right, you missed one detail. So let me explain how the writers are blocking the reader. Let's say writer has come along. There are no readers when the writer comes in. Writer goes and starts doing a long write. Okay? While the writer is writing, the first reader comes along. Okay? Is going to go in, okay? The mutex, it will grab the mutex, it will increment the read count. The read count goes from 0 to 1. You say, am I the first reader? Okay? You say, yes, I am the first reader. There is no other reader. Okay? So now you say, if I am the first reader, it's my job to block the writer. Okay? So you try to go and do wait in order to block the writers. Okay? But in doing so, you block yourself because the write semaphore also has been decremented by the first reader already. So it's gone to 0. So when you do wait, it goes negative. Okay? Okay? So if you are the first reader and there's no writer, you explicitly block the writer. If you're the first reader and there's already a writer, in trying to block the writer, you block yourself here. Okay, because the writer would take that weight, the first weight here, and the first weight there has actually decremented it from 1 to 0. This weight, in trying to block the writer, decrements it further and makes it -1. And our semaphore definition says if the semaphore is negative, you block. Okay? But in trying to block the writer, basically a writer has actually blocked you because it has gone and grabbed that semaphore already. Okay? This is simply a binary semaphore. Okay? So you will block. So this reader, the first reader blocks here. Okay? Now let's say second reader comes along. Writer is still writing because it's a long write. Okay? All readers have to block. Okay? So now the second reader is actually going to block on this mutex itself. It cannot even go in because the first reader is blocked here on the wait. It still holds the mutex lock. All subsequent readers will block here. Somewhat subtle, but you need to understand that writers are actually explicitly blocking readers without writing any code to block them. Is that clear, or should I explain again? Okay, just to recap, when the first writer, if the writer is the first one to come into the system, it gets to go in and write, and it does wait on the write semaphore. The semaphore goes from 1 to 0. Okay. Now, if the reader comes along, it will increment the read count. Okay, it goes to 1, and it has to try to say, I am the first reader, so I have to block the writer. So it tries to do a wait on the write semaphore, but it's already held by the writer. So in trying to block the writer, it itself blocks. Okay. And then any subsequent readers won't even get this far there because the first reader that has actually been blocked is still holding this mutex lock. Okay, because you have blocked here, you haven't done a signal. So all subsequent ones will block on the first line of that method. Okay, so writers are actually blocking the readers. Okay, and then when the first writer leaves, it will do a signal that will cause the reader to come and be unblocked because it was blocked here. So it will go in, and then it does a mutex signal that will block all of the other readers one at a time, and they'll all go in parallel. Okay, so you do get parallelism for readers as well. Okay. So now it should be clear that we have a solution to the reader-writer problem. Okay. We should ask, is this a good solution? So that's the part that we haven't yet asked. Okay, so basically what we will say is so this is a discussion which says that why it works. I just explained it in code. Okay, and then the only thing that we haven't done is what was sort of asked very early on as part of the correctness criteria. Is this a fair solution? Right? And we'll say the solution is not fair because the solution we put up here explicitly favors readers. Okay, you can actually have a starvation issue where the readers keep coming into the system. There's a blocked writer, and the readers are just going in. Okay? The read count is never 0. So a blocked writer will actually never unblock because as each reader leaves, another reader comes along. Okay? That is the fact that there is a blocked writer and it has to be given a chance to do the writing is not being considered here. Readers would continuously come in, and so long as the read count always stays non-zero, it doesn't matter how many writers are still waiting. Okay? All these readers that have come later are still getting to go in. Okay? Because reader comes along, says read count 0. No, it's not 0. Go and start reading. That's it. The writer is blocked. Cannot do anything about that. Okay? This reader that came along later is still getting favored over a blocked writer. So you understand why it's not fair, right? It's correct code, but it is favoring readers over writers. Okay, so it's not necessarily fair to both readers and writers. Okay, so here is another solution. This one tries to favor some writers. It's not fair either, but it's a lot of flips. You can actually make it fair, but that's more complicated. We will not go into as much here. Okay, so here is the code for write. So there's the. Okay, so here basically you have write mutex, okay? And there is basically, so this was the old code for write. Okay? So you just grab a lock, perform the write, unblock. Okay? Now we added some extra code to track the number of writers that have come in. Okay? So each writer is going to go and increment it just to say, is there some other writer waiting? Okay? And if you are the first writer, you are going to go block the readers, okay? Which is what you want to do anyway. Okay? So what this essentially does is the writer comes and it waits. Okay? By doing this, you have blocked additional readers. All the readers that have gone in are in. Okay? They are reading. But as soon as the first writer comes along, he says, I am in queue. If any reader comes in after me, it shouldn't go in. Okay? So I'm going to explicitly block them. Just as the readers could block the writers in the previous solution, here the writer says, as soon as I come in, I'm the first writer, I'm going to make the other readers wait. Okay, so you block the readers here. Okay. And then if you're the last writer, you say, I let the readers read. Okay. But because you did this, you are now favoring writers because once you block the readers, writers can come in one at a time and still do writing. Okay. Only after all the writers are finished will you unblock the readers. Once the readers block, you keep them blocked until all the writers are finished and the last writer has left. At that point, you unblock them and they all get to go in parallel. So it's somewhat more fair. The readers will block the writers as they rightly should. But once the first writer comes along, there is no parallelism anymore. You say that stand in a queue. Okay? But it's not totally fair because the writers are not going to unblock all the pending readers until they are all done with the writing. This is why it is still favoring writers, not completely fair. Once you have a queue, if you actually service the queue in FCFS order, then you will have a very fair solution. Yeah, this one is still not doing that. So the right thing to have done, which there is no code here, but I will explain conceptually. If this is the queue of all waiting threads, okay, so once the writer comes along, there is no parallelism, so you block readers. So let's say a reader, there's a reader. Then there's another writer, then there's some more readers queued up. So this is the order of arrival. What you should do is then you should let this writer go. Okay? Then you let the next batch of waiting readers go, which is these three. They do parallel reads. Okay? Then this writer should go and it should do its own write. Then you let the next batch of readers read in parallel and then the next writer and so on. If you do this, you have a fair solution. All readers that come in a batch get to do things in parallel. When a writer comes along, it gets to go in the order in which it came into the system. Right? So this is the right, fair way to do it. Right? Neither of the solutions we had actually does this. Okay? The first one simply blocked all the readers. I mean, once a writer comes, all of these guys can still go in if there's a pending reader. So they get to jump the queue. Okay? Here, once you block the readers are jumping the queue. Or the writers are jumping the queue. So it favors writers. So we didn't make it very fair in either direction. Okay? So that's something to keep in mind. They're all correct. They won't violate our correctness properties, but they're not fair. Okay? Okay, so let's skip the scenario. So that was all complicated code. Okay, you could do this in Java in a very trivial way. Okay, just a few lines of code. Okay, so basically here is this is your read method. Okay, not synchronized. You make the read method synchronized, you don't get any parallelism. All the read, you will all block. You'll have only one reading happening at a time. So all you do is you basically you don't make this method synchronized. The write method is still synchronized. Okay? The read method is not. Okay, you say prepare to read and done reading. So you call a prepare to read method which is there, done reading method which is here. Okay? These two methods, they're simply doing whatever we had done before. You increment the read count. Okay, here you basically increment the read count. You say while the number of writers is greater than 0, you wait, otherwise you increment the read count. Okay? So if there is any writer you are blocking, so this is the solution that favors writers. So if there's already a writer waiting, you won't let any parallelism happen, you just wait. Otherwise, if there are no writers in the system, then you just simply increment the read count and just come and start reading in parallel. Okay? And here, as each reader leaves the system, you basically say, I'm going to decrement the reader. If I'm the last reader, I wake up all the threads that are blocked on this condition variable. Right? So this is a condition variable wait, and that's a condition variable notify. Okay, much simpler code. The only thing to realize is you will not make this read synchronized. Okay? This is the right code, which you will see is synchronized. Yes, question.
On the last slide, you have prepared to read as synchronized.
Yes.
Do you need to call after the while loop thing? Because I guess that just for resources. Like if you didn't get rid of the wait, it would effectively be the same.
Are you saying here you need a while? No. Here you need a while? Is that what you just said?
That while.
Here, what's the point?
So I got rid of wait. The wait at the while loop. Yeah, that effectively be the same outcome. That just wastes resources.
So if you get rid of this while, you are going to have a solution that will favor. This while is only because you remember this is a Mesa-style semaphore. So you basically just check whether just the write count is still greater than 0. If you want a solution that favors readers, all you're simply going to do is increment the number of readers, go do the reading, and then once you basically are the last reader, you're going to wake up the writer. That's all you will do. Okay? Just to make it a little more fair, you also check if I am a reader that is trying to enter the read method, if there is some other writer waiting, okay, I will also wait. I will try to do this. Okay, so if there's a writer waiting, the write count is non-zero, is greater than 0. So you make the readers wait here. That's all is trying to do. Okay, does that answer your question? No, I'm not sure that that's what you asked.
So after the while loop, there's a wait.
This is just one statement. This is not inside the while.
Right, no, yeah. So if I got rid of the wait,
Yes.
would the outcome be the same?
If you get rid of the wait, you will have a solution that favors readers. It won't be the same. Because what would happen if you get rid of the wait is readers are just going in and reading. Whether there's a writer waiting or not, if there's a writer waiting, these readers will still go in and start reading. Okay? All this statement is doing is, if there's a writer waiting, subsequent readers are made to block. They don't get to go in. So they're reducing read parallelism in the interest of fairness. Okay, read concurrency has gone down. If you remove it, you will still have a correct solution. Only thing is you are going to let the readers go in independent of whether there are writers waiting. That's all that's happening. Okay. Here is the write method. So the thing to realize is the write method is synchronized. Only one writer at a time. Okay. So that basically is synchronized, only one writer. So So you do prepare to write, do the writing. So this whole thing is protected by this synchronized lock. You don't need to have any locks here because the method itself is guaranteeing a lock. So only one writer will do the writing, but you also do the prepare to write and done writing where the first writer goes and increments the write count. This will cause any for subsequent readers to block. Okay? And it says that if there are no readers, if the reader count is greater than 0, wake up. When you're done writing, you're basically going to decrement the number of writers and simply wake up any threads and let them figure out what to do. Okay, let the first thread figure out what the right thing is to do. Okay, so here you do have a synchronized method. Okay, in the previous case, the read method was not synchronized. Okay, let me ask a quick question. Why are these two methods not synchronized? Okay, in the previous code here, okay, this method wasn't synchronized, but the prepare to read and done reading were actually synchronized. You put the synchronized keyword here. So why is prepare to write and done writing not synchronized? Yes.
They are synchronized. They were just called in the parent method that's called the prepare to write method.
Okay.
The sum write method.
Okay, so the point being made is you don't have to put synchronized here because they're always called within another synchronized method, and by definition that already has the lock. Right? In fact, if you put synchronized there, you're going to actually have a deadlock because there's a thread that already holds a lock that's trying to reacquire the lock in another method. Okay, and you will block. Okay, so if you are inside a synchronized method, you should never call another synchronized method as a matter of writing correct Java code. One synchronized method calls another synchronized method, guaranteed deadlock. Code will not work. The first synchronized method has the lock, which is why it's actually executing in that method. And you call another synchronized method that will try to reacquire that lock. Remember, a synchronized method internally always tries to grab the lock. You hold it once, you shouldn't try to grab it again. You already hold it to begin with. Okay, so these two methods here are already synchronized. Number one, because you're calling them from another parent synchronized method. Okay, so they are synchronized, and in fact, you shouldn't make them synchronized again. That will result in incorrect code. Okay, some simple subtleties to keep in mind when you write Java code. Okay. Any questions? Okay, so now the good news is that was the implementation of readers and writers. Now, if you actually need to implement reader writers and get more concurrency, there is something called a read-write lock that is supported out of the box in Java. Instead of calling lock acquire and lock release, you basically say read lock acquire and read lock release and write lock acquire and write lock release. Okay? And it will do exactly what we said. When you do a read lock acquire, if the other readers are reading, you will immediately get the lock. You won't block. Okay? When you do a write lock acquire, or when you acquire the lock in write mode, all other readers and writers will be blocked. Right? So there's an implementation of locks that has been generalized to support readers and writers for you. So all the code that we saw would actually implement this method. Okay? But in reality, if you want to simply read concurrency for your threads, rather than using a normal lock, you use what is called a read-write lock. That will give you the same properties that we just talked about. Okay, so the whole exercise that we did, in some sense, you will never have to do in reality because you will simply use the built-in read and write locks in your code. Okay. But they should show you how read-write locks are implemented. Okay. Same is true of C and C++ code. Okay. P-threads, which is POSIX threads, also support, in addition to normal locks, they also support read-write locks. Okay, so you can always get the lock in read mode or write mode. If you get a lock in read mode, that means your readers, you have concurrency. You get a lock in write mode, you have mutual exclusion. Everyone else is blocked. And you hope that these implementations do the fair thing, which is this. That you wouldn't write code that favors readers or writers because that will basically trade correctness for fairness. Okay? So if you have to write code, real Java code that requires readers or writers, you don't have to write all of the code that we just went through. You simply declare a read lock or a write lock using this class, read write lock class, and you do the right thing in terms of acquiring and releasing. Okay. So that is all we will say about readers and writers. Next problem up is dining philosopher's problem. It's an interesting problem, different problem that from what we've encountered. Okay, the problem is pictorially depicted there. Okay, so we'll assume that there is a group of n philosophers who are sitting around a table. Okay? And abstractly, these philosophers can do only one of three things. They can think and philosophize. Okay? They can get hungry and they can eat when they're hungry. Okay, and this is how the table is arranged. Okay, they're basically each given a plate of spaghetti. Okay, and they're given forks to eat. Okay, some books say chopstick, some books say fork. I don't like either one, but we'll assume it's a fork or a chopstick. And we assume that to eat this spaghetti, you actually need to get either two forks or two chopsticks for sure. I mean, both the one on your left and one on your right. Okay, so if you get two, then you get to eat. If you get only one or you get neither, you don't eat. Okay, so these philosophers have some table manners at least. Okay, so the problem is as follows. You'll see that the chopstick or a fork is shared between a philosopher and his or her neighbor. Okay, so now if you become hungry, you have to go and try to get your left and right fork. If your neighbors are hungry and already eating, you're out of luck because those forks will be in use. Okay, so you can't eat. You have to wait for somebody to have finished eating. And then when they put it down, you get to eat. After you've gotten both the forks. Okay, so the dining philosopher problem is essentially showing you how to acquire shared resources. The shared resource here is essentially the chopstick or a fork. And you need both you need two explicitly, the left one and the right one, in order to achieve your task. Okay, so it's saying that you cannot just go and reach across the table and grab somebody else's. Not allowed. You can only do your left one and the right one. Okay. So now the question is, you don't want the philosophers to starve to death. If they get hungry, they better eat because they only do thinking and eating. Yeah, and then when they get hungry, they want to eat. So how do you come up with correct code where when a philosopher actually becomes hungry, that they will eventually get forks to eat, and they won't be kept waiting all at once. Okay, is that clear? What the problem is? Yes.
Can we do round robin?
Okay, can you do round robin? Okay, the first question. So you are saying, let us assume that each philosopher gets a turn. Okay, if it's a philosopher 1, are you hungry? If you're not hungry, then it's a philosopher 2, are you hungry? Okay. You could certainly do that, but you have to realize that if you are doing round robin in turns, you are not getting any concurrency. Okay, that's a correct solution, but you haven't gotten any concurrency because if this philosopher is hungry and this philosopher is hungry, they should be able to eat in parallel because they are not sharing forks. So whenever independent philosophers that don't share any resources get hungry, you want to allow concurrency. Okay, if you just simply take turns, you just have global lock. Okay, what you just said is essentially a global lock. So you just say, philosopher hungry, grab a global lock that only one philosopher eats at a time, and that would be a correct solution, but doesn't get your concurrent solution. So you want to maximize your concurrence. Okay, the only time you should actually block when you're hungry is if one of your neighbor or both are eating. That's the only time you cannot grab the phone. Okay. This is the first solution. Okay, so basically this is going to use semaphores. You have a semaphore for each chopstick or a fork. Okay, so you have an array of semaphores there. Okay, so chopstick I is a semaphore for the ith chopstick. Okay, so basically all you're doing is you wait for the left one, you wait for the right one. You try to grab the left one, you grab the right one, and then you basically eat, and then you release the left one, you release the right one. Okay, yes?
If you do this, and then everybody gets to left chopstick, and everybody gets right chopstick, that comes.
Okay, so what is being pointed out is this solution looks very simple. It says grab a lock on the left one, grab a lock on the right one, and eat. Okay. Now, what was pointed out is if they all become hungry at the same time, they all reach for their left chopstick, and let's say they all get it, because initially all the chopsticks are on the table. So they all pick up one chopstick and they all reach for the right one, and the right one is gone. Okay, now they are going to starve to death because each one is waiting for someone else to finish. No one is going to finish because everyone has only one. Okay, so now you have starved our philosophers to death. That's not a good solution. Okay. So here is another one, and this one actually works. It looks a little more complicated. It's not really. This is Java code. We made it a monitor. Okay, and this is essentially. So initially we make everyone think. They randomly become hungry, and when they become hungry, what they do is. So what you want to do is actually check what has happened to my left and what's happened to my right chopstick and make a decision. You don't just grab it and then say, I'm now going to grab the other one. You actually have to check, are both available? And if so, then I'll grab both and I'm done. If either one is not available, I wait politely for my neighbor to finish. That's the way to do it. Okay? Is that clear? So what you want is not just grab something, but check and say both are available at the same time. I'm going to grab them and start eating. If one of them is not available, I'm going to wait. Okay? That is essentially what this test does. The test is not going to block you. What it says is my left neighbor eating. Okay? And I am hungry and my right neighbor is eating. That basically means that it's actually not eating. Okay? If the left neighbor is not eating, the right neighbor is not eating, and I am hungry, that means that both chopsticks are available, so I start eating. And if, is that clear what happens? So and this is what happens when you do pickup. Okay? So you essentially say, if I am going to go into a hungry state, I do test of I. Okay? If I come out of test of I, basically it says that I am done. Okay? I have basically checked that neither of my neighbors are eating, and then you're done. You start eating, and then you say, if I did not grab the fork, if any one of them was eating, then I wait. Okay, so essentially all it's checking is, are both of my neighbors not eating, in which case I basically grab the forks and eating. Okay? And if either of them one eats, then you won't come out of that with the eating state, so you will basically just block yourself, saying one of them is busy, so I'm going to politely wait for one of them to finish. Okay? And when you release, you essentially say, I'm going to go back to thinking state and I check, is my right neighbor hungry? Right? If so, I will let him figure out whether now he has 2 forks. So I call test for my right neighbor. Okay? That will recheck that for my right neighbor. Okay? Saying is that, and then it will check if that right neighbors, both neighbors are all available, then it will go start eating. Okay? So whenever I put down my fork, I do the check on my left and right neighbor. If either of them are hungry, then they will get to eat. Okay? Is that clear? What's going on? So the basic point is you don't want to just. So what we did here is often. I mean, this looks like some triviality where you just did this, but this often happens. Okay, when you are trying to acquire locks on multiple resources, and you need locks on multiple resources to do something. Okay, this often happen in databases, for instance, where you have to lock records, and if a query touches multiple records and you have to grab it all, and there are multiple queries running, you will have this kind of problem. You grab a lock and then you wait for another lock. If all queries that are running do the same thing, they will all deadlock. Okay? So it's better to first check the lock state, okay, which is essentially what we did here in test. We first said, are those locks that I want available? If so, I grab them all at once. Otherwise, I'm going to wait until something becomes available and wake up at later time and retry. That is what we did here. Okay? So this is conceptually a good way of writing code when you need multiple locks. In more complicated synchronization problems, this often happens. You need multiple locks to achieve something. In databases, this happens all the time. There are locks on tables, there are locks on records, there are locks on indices. Okay, to execute a query, you may need to grab multiple locks. If you just try to grab one and wait for another one, this kind of problem will occur frequently, and you will have deadlock in your system. Right? Although this looks like a trivial, cute problem or a funny problem, it actually has some real world implications on how people actually write bad code and get into all sorts of trouble. And there are better ways to do this, which is you would first check if you have the right resources in hand and only then proceed. Don't grab some resources and wait for other resources. That could potentially lead to a deadlock unless you do things in the right way. When we talk about deadlocks in a class or two from now, you will see. that doing this kind of stuff always gets us into trouble. Okay? All right, so I think we have a minute, so I'm going to very quickly show you code using that was code using monitors. Here's code using semaphores. Okay, so again you have an array of semaphores, and you are going to basically do these checks that I mentioned. Okay, you are basically going to say, I am a philosopher, I'm thinking, once I'm done thinking, I'm going to try to grab 2 forks. Okay, is 2 forks or blocked? You never say I grab 1 fork and wait. Either I grab both forks, or if any one of them is busy, I block. That is what the take forks do. Okay, then you eat, which is basically you're eating, and then you put both forks on the table. Okay, so the main method, as you can imagine, is the take forks method, which basically says I have a lock, okay, a mutex lock, I change my state to hungry, okay, and I check. Okay, I'm going to try to do the test, which is the same code I showed you previously. Okay, this test is going to check, atomically check, is my left fork available, is my right fork available? If so, I'm done. Otherwise, I'm going to block. Okay, so this is basically the key concept that is repeating from the old code. So you always check the left and the right. Okay, and then you grab both, or you grab neither, and then you just simply block. Okay, but now done using semaphores. Okay, so with that we will end it here today. Okay, there is a class on Monday. I'll do quick review of for the midterm on Monday. Okay, and some other material. Exam is on Tuesday. Lectures 1 through 8 for those of you who came in late is on the test.